Hey everybody. So we are continuing to talk about maximums and minimums, extrema. In the previous videos, we talked about absolute maximums and minimums, right? These points that are larger or smaller, the values, the output values is greater than or equal to every other value of the function, or less than or equal to every other value of the function if it's a max or a min. So here I've got a fun little function, and I can point out there's a absolute maximum. So this, you can see it has looks like it might have a horizontal asymptote at around 2. It's not quite that, but it is a horizontal asymptote. It's never getting larger than this. So let's just assume this picture is the whole function. This is the absolute maximum then, right? It's the greatest value the function achieves. And then we see this point here is the absolute minimum, the least value that this function achieves, at least if the function continues as it appears to here. However, these absolute max and mins aren't the only things that are relevant. You might notice we have other kind of interesting similar types of spots here that we can maybe describe as the tops of hills and the bottoms of valleys, right? This minimum is the bottom of a valley. This absolute maximum is the top of a hill. These points in this point in here is the top of a hill. This point here is the bottom of a valley. Also, those points are clearly not the smallest or the greatest value the function takes on. So they're not absolute maximum minimums, but there's still something fundamentally special about them, right? There's something interesting about being at the top or the bottom of this little section. And so we give those a name, and that's what we're going to begin today's conversation about. We call these local maximums. Maximums and minimums, all right, or local extrema. So let's start with a definition and then get some more ideas in here. So our definition is going to be, we'll say a function f has a local maximum at x equals c, so some value, if, so I'm going to say it this way. There's different ways to state this. I'm going to say if f of x, if f of c is greater than or equal to f of x for all x near c. So what I mean by near c, all right, so when I write near c, we can think of this as meaning on an open interval containing c. Okay, so that's what I mean by near c, some open interval. It doesn't say anything about the size. So near, I'm using in a little bit different of a way than we're used to. This interval could be massive. In fact, it could be infinite, in fact, and we'd still call it near, because all I mean really is an open interval. Typically, the ones we're going to talk about are going to be small. We'll say more about what this means in 1 second. Let's define a local min. We'll say a function f has a local minimum at x equals c if f of c is less than or equal to f of x for all x near c, right, with the same meaning. So what does this mean? Let's do a little sketch. If I have all right, here's a function. And let's put in an axis. Let's start with c being some value right here, right? What I'm looking at is this point, so if this is f of x, this point here, c, f of c, it's not the smallest value of the function, right? We can clearly see, for instance, there is lower. There's also lower values over here. In fact, all these outputs down here and over here are lower, right? There's lots and lots of places where the outputs of the function are less than c. But if I restrict myself to some open interval, so for instance, if I look at the values near c, so I'm coming up with an open interval, I can go to about here. If you look at this interval, any value of the function, right? So I'd be looking at this section of the function above that interval. All the output values are greater than f of c right here. That point is a local minimum, right? Because there's an open interval that exists where this is true, where it's the smallest value, right? So that's what we mean by near c, right? This can be as small as we want, right? Here's an extreme example. If I take, here's another function, right? If this is my point c, as long as I restrict myself, right, somewhere about here to here, so something like this little interval around it, it's the smallest value around, right? Clearly, we get much lower as we go away, but right there, it plays a special role. It's the smallest value, right? A similar thing can happen with local maximums, right? I could have something like this. Here's a function like a strange w. This point here is a local maximum because if we stick into this little interval around it, right? Something that, right, this, let's do another color. If we look at just this portion of the graph, it's the highest value around. Of course, as soon as we go outside that interval, things get much different, but that would be a local maximum, right? So if we go back to this graph, right, notice this is this point right here. This is the lowest value until we get to about here. And then on this side, of course, well, it can go, it's not clear from the graph when it goes below, if it does at all. It's not clear, right? So I don't know for sure when the interval has to end, but it's clear that an interval exists. And I don't need to get the whole interval. Certainly it's true that if I stay on the section of the graph that I've covered so far, this is the lowest point around. We can do a similar thing here. This is the highest point around. In fact, the absolute max and absolute minimum are also local minimums, because certainly this is the highest point on some interval nearby, and this is the lowest point on some interval nearby. Turns out the interval happens to be the entire function, but it still satisfies the definition of a local maximum or minimum. So a local maximum or minimum is not necessarily an extreme or an absolute maximum or minimum, but an absolute maximum are also local maximums and minimums. Okay, let's clear this, go back to our other page. So before we talk more about finding these things, let's just make a quick let's just quickly say why we might care about them. These places are special, right? So for instance, let's imagine, let's make a very literal interpretation of this graph and say it's a graph of a hill, right? So it's got the shape of a hill. If we were going to place something on this hill, like a ball, right, knowing where max and minimums are tells us what's going to happen to the ball when we place it there. For instance, if I place a ball on this hill here where it's not a maximum or minimum, we can see what's going to happen. It's going to roll down. It's going to move from that spot rather quickly. If I place the ball here, it's going to stay where it's at. Likewise, if I place the ball here or here, or here, it's going to stay where it's at. Even more in this particular example, right, we might be curious about minimums because while at this maximum and this minimum in both places, if we set the ball right there, it's going to stay there. In this maximum, if a gust of wind came along, depending on the direction, it might easily blow this ball down the hill in either direction, whereas this one is relatively stable. It would take quite a bit of disruption to move that ball out of that little divot, right? Similar for the top of the hill here and the bottom of the hill here, right? So of course, this is a little silly. Why do we care about placing a ball? But this has, this analogy can extend to things like chemical reactions and places where they have low energy or high energy. And depending on the situation, you might have something where a small change in the situation leads to great changes in the outcome, right? So a small change here, if you shake this ball at the top of the hill a little bit, it ends up at a dramatically different place. In the terms of a chemical reaction, that means maybe if you change the temperature slightly, given some conditions, you might end up with an explosion, where if you have different conditions, like the bottom, a local minimum, changing the temperature slightly might not do much. The ball might wobble a little bit, but it'll settle back to where it was. The chemical reaction might have some kind of dynamic thing happening, but then it settles back down to wherever it was at. Okay, let's think of one other example. Maybe let's look at this picture here again. Maybe this is some kind of cost function for a business. And of course, we would want to minimize cost, right? So this might be the minimum place, but maybe minimizing cost requires a certain kind of factory that we don't have access to yet. Okay, so maybe whatever this graph is graphing, this 6 of whatever is happening on this graph right here isn't available to us. So we can't actually get the absolute minimum, but we say, okay, but we're able to get to here, and that's the next best lowest place. That's our local minimum where we can achieve not the lowest cost, but the lowest cost possible to us, right? So that might be something that we are interested in. Okay, how do we find them? Well, let's use some intuition from these pictures. If I look at all the places that I'm calling local maximums and local minimums, and I imagine the tangent lines at them. So here's one here. Here's one here. All right, there's one there. Do one more. Right, if we imagine what these tangent lines are, it's not hard to imagine that these tangent lines should be horizontal, right? Even these little tiny spots in here and in here, can't really see with that one. And this turns out to be pretty good intuition, okay? That if we have a local max, a local max or a local min, let's try that again. Right, that we should get a horizontal tangent line. This is almost true. It's, let's say, mostly true, which is kind of a nonsense statement. It could also be the case that we have a situation like this. Maybe like think of an absolute value function if we inverted it. It's got a maximum at this point, but there's no tangent line at that peak. In fact, the derivative doesn't exist. And it turns out that these are the two possibilities we have at local maximums or local minimums, that we will have a derivative equal to 0 or does not exist. Okay, so let's see if we can prove this a little bit better without relying on intuition from graphs. It's great to have it and use it to know where we need to go next, but we can actually make this a little more solid with something called Fermat's theorem. And this theorem simply says that if f has a local extrema at C, and f is differentiable at C, then f prime of C is equal to 0. So this theorem that we'll prove in just a second, and it's fairly straightforward to prove, tells us that if it's differentiable, if we have an extrema and it's differentiable, then the derivative must exist and it must be 0. So that tells us that if well, just what it said, that the derivative must be 0 if it exists. It doesn't tell us that it has to exist. So that leaves us with two possibilities. It leaves us with two possibilities, that at an extreme point, or a point of extrema, the derivative is 0, or the derivative does not exist. Okay, that's the conclusion we can come from this theorem that we're about to prove, because if it does exist, it must be 0. So the only other possibility is it doesn't exist. And because we're often looking for extrema, we're going to call points where the derivative is 0 or does not exist, we will call these critical points. Okay, so let's prove this theorem and then come back to some critical points. So how do we prove this? Let's assume, or let's say, suppose f of x has a local maximum at x equals c, and f of x is differentiable there. Right, so we're assuming that it has a maximum there. We'll talk about minimums in a second. We got to handle them separately, and that it's differentiable there. So then we know two things. Since it's a maximum, or local max, since f of x is a local max at C, f of c is greater than or equal to f of x near C, right? So meaning on some open interval. So we've got that fact in our pocket. That's just the definition of being a local max. We also know that f prime of C exists. It's equal to the limit as h goes to 0. Sorry, I want to use the alternate statement for this. It's just easier to see. As x goes to C of f of x minus f of c over x minus c, right? That's just one of the formations of the definition of the derivative. We know that this exists, so just write that. The fact that it exists means that the left-handed and right-handed limits exist and they're equal to each other. In other words, whatever number f prime of c is, it must be equal to the limit as we approach c from above. But what can we say about approaching it from above? Well, if c if x is greater than c, right, we're approaching c from above, x is greater than c, the denominator here is positive because we've got of x minus c, a positive number. X is greater than c, x minus c is positive. But we know that f of x minus f of c has got to be either 0 or negative, because f of c must be greater than f of x, or equal to. If they're equal, it's 0. If f of c is greater, the numerator is negative. So this thing must be less than or equal to 0. In a similar way, we know that the derivative is also equal to the limit as we approach c from below. Right? So now x minus c is negative because x is below c. You're taking a smaller number and subtracting a larger one, you get something negative, but the numerator stays the same. F of c is bigger than or equal to f of x regardless of which direction we approach it from. So if the bottom's negative and the top is negative or 0, the whole thing must be positive or 0, greater than or equal to 0. Well, what does this mean? This means that, so f prime of c is greater than or equal to 0, and f prime of c is less than or equal to 0. And there's exactly one number that is both less than or equal to 0 and greater than or equal to 0, and that number is 0, right? We have to take that equal part because these both have to be true. For us to have a maximum here and the derivative to exist, both of these have to be true, so the derivative must be 0, okay? We did it for local max. You can do the same thing for the local minimum, just some of these inequalities turn around. I'll let you think that through. I'll just say similar if f of c is a local min. And we'll consider it proved. Okay, so this is a nice reality. We've been playing with this idea intuitively for a while. The notion of horizontal tangents and seeing these little hills and valleys and things like that. But now we've put a little more precision to it. Okay. So what we get to take away from this is what I put up here. So let's simplify this. That extrema, when you have extrema, max or mins, you must have a critical point, right? Because only one of two things is possible at these max or mins. The derivative exists, and by Fermat's theorem, it must be 0, or it doesn't exist. And that covers what critical points are. Derivatives are 0 or derivatives do not exist. So let's do an example, finding some critical points. Suppose I have the function g of x is equal to x squared, x minus 2 cubed. And I want to find the critical points of this function. Okay, so what it means I want to do, say find critical points. F prime of c equals 0, or derivative does not exist at c. All right, so we want to find points that satisfy one of those two things. So a good place to start is, let's take the derivative. So we can multiply this out and get a polynomial. It'd be an easy derivative to take, but multiplying out that cubic seems annoying. So instead, I'm just going to use the product rule here. G prime of x, right? I've got two functions, x squared and x minus 2 cubed. So x squared has a derivative of 2x. I leave the x minus 2 cubed alone. Then I leave x squared alone. And I take the derivative of x minus 2 cubed. Now we have a chain rule. I've got this inner function, and the outer function being cubed is my outer function. So I take the derivative of the outer function. I take that 3 down. I have a squared here. The derivative of the inner function is pretty straightforward, though. It's just x minus 2's derivative is 1. So we're multiplying by 1. I don't need to write anything. And now let's factor this. Notice both of these terms have a factor of x and x minus 2 squared. Leaving behind, in the first term, we have a 2 and another factor of x minus 2. Plus, it looks like I have a factor of 3 and one of my x's is left. So I've got 3x, and I can simplify what's inside that parentheses at the end there as I've got 2x plus 3x is 5x, and then there's a minus 4. So there's my derivative, right? The advantage to doing that product rule, it turns out, is besides not having to expand that thing, I didn't have to factor it because my next step is to decide where this derivative doesn't exist or is equal to 0. Doesn't exist is simple. This is a polynomial. polynomials exist everywhere. So the derivative exists everywhere. So none of my critical points are places where the derivative doesn't exist. They must be points where the derivative is equal to 0. Now I see how nice it is to have this in factored form, because it's easy to find zeros in that form, right? We have to solve this equation. G prime of x is equal to 0. In other words, whereas x times x minus 2 squared times 5x minus 4 equal to 0. And that is simple enough. That happens when x is equal to 0, when x is equal to 2, or x is equal to 4/5 or 0.8, right? Just the zeros of each of those factors. And so these are the critical points of this function, right? So let's remind ourselves what these critical points tell us. We said extrema, if there's an extrema, a local max or a minimum, it must be a critical point. So any maximums or minimums must happen at one of these 3 points. Let's jump to a graph. Here's the graph of f. Notice there's x equals 0, there's x equals 0.8, and there's x equals 2. From this picture, it's clear, right? Looking at 0, 0, our function is, there's the top of the hill right there. That's a local maximum. At 0.8, we're down in the valley. We got the bottom of a valley, and that's a local minimum. But something funny happens at 2. You can imagine the tangent line here does have a slope of 0. The derivative is 0, right? It's kind of flattens out right there. But it's not a maximum or a minimum. The points to the left are smaller, right? You can see the function going down. Maybe we zoom way, way, way in, right? It's very, very flat, but they're the points over here, right? At 2, it's equal to 0. Oh, the computer doesn't have enough resolution. It's calling these all 0, but they're actually slightly smaller. And you can see they start getting negative over here. Similar thing on this side. They're increasing, right? So there's no interval, right? If I try to draw an interval, remember that idea of being a max or a min, you have to have an open interval around the point where it's either the biggest or the smallest. If I try to draw any interval, right, it has to be around it. The points on the left are smaller, the points on the right are bigger, so it's neither a max or a min. It's neither of those, right? So looking at our 3 points again, the critical point 0, 0 is a local max. The critical point 0.8 negative, it's called -1-ish, is a local min. The 0.20 is neither. So first, that tells us this was great. We used critical points to locate a couple of extrema. We also should notice that this arrow of indication, right? What I'm saying here, if you have extrema, you must have critical points, does not go the other way. You can have critical points without implying extrema, right? That's what we just saw. The critical point at x equals 2 does not indicate a max or a minimum. What critical points do for us give us candidates for max, local max and mins, right? They don't have to be local max and mins, but they might be, and they're places worth investigating. Okay, so right now we're using a graph to find out where max and mins are. This is not always going to be possible, right? For instance, let's go back to that first example. We noted that we had a local max here, local min here, an absolute and local max here, an absolute and local min there. But there's actually a point right here that's very hard to see on the graph. That's a local maximum. If we draw in, there's a tangent line right there. If I zoom in, it helps us see perhaps that that point somewhere in here at whatever 6.728 is a local maximum. Everything near it is getting smaller, right? If you go away from it, you inevitably get less of an output value. That wasn't entirely clear when we were looking at our graph, right? So you can't rely on looking at a graph. It's not always obvious. You don't know if you've looked everywhere. You don't know, how good the resolution is. You can't always rely on your software or if you're graphing it by hand. So we need some better methods for doing this. So let's investigate one of those. We'll have a few. The first one has to do with having closed intervals. So location of absolute max or min on a closed interval. Okay, so if f is continuous on a closed and bounded interval, and there's some technical things there about why we need bounded, but for us, this is going to mostly mean a closed interval is going to be something of the form A and B. It's technically not true. There's more you can do. You can have this is like the building block of closed intervals, but you can have different kinds of closed intervals. But we're only going to look at these for the time being. So we don't really need to worry too much about bounded. Bounded just means it's within some values. It doesn't get too large or too small. That's a good way to think about it. And since this is a single interval, it's always going to be bounded, right? It's not going off to infinity somehow because it's stagnant. So anyways, we've got a closed interval. Our function is continuous on it. We'll call this I. Then any maximums, minimums of f over I must be at the endpoints x equals A or x equals B, or at critical points on I. Okay, so if we have a function on a closed interval, we're not going to prove this, but we're just going to intuit a little bit. If we have a closed interval, our function is defined and continuous on, any maximums or minimums have to be either at the endpoints or critical points, right? So let's look at a point that's not a critical point, something like this, right? Well, if it's not a local max, if it's not a critical point, then it's not a local max or local minimum. And some of the points are going to be bigger than it, some points are going to be less than it. So how can it be a maximum or minimum, right? So we have to look at those critical points to find the absolute maximum and absolute minimum. In this case, we have an absolute maximum there. However, at the endpoints, these endpoints might not be critical points, right? If this function continued on, but we're just closing off part of the interval, it's not a zero of the derivative, right? The derivative might exist there, but it's at the end point, so we're sort of insisting that it be a minimum because all the points that would continue on below, we've cut off that part of the function. So when we're looking at a closed interval, all we have to do is look at the endpoints and the critical points. And so this gives us a strategy to find the absolute max and min on a closed interval, AB, right? All you have to do is evaluate on the endpoints, find the critical points and evaluate and compare. Right, so if we were doing this problem here, we would evaluate the endpoint here, the endpoint here, the critical point here, critical point here, the critical point here, the critical point here, and the critical point here, and we would find this is the smallest value, so it's the absolute min. This is the biggest value, so it's the absolute max, right? All these other points, those are all local maximums and minimums. And then we have the other endpoint. We don't know yet how to tell without a graph whether they're local max or local mins, but it doesn't matter to us. We're just looking for the biggest value and the smallest value. And since we know the only places those can happen are the critical points and the endpoints, all we have to do is check those and compare. So let's finish with an example of doing that. This will be the last one in this longer than I anticipated video. Let's find the absolute extrema, absolute max and mins for f of x equals x cubed minus 6x squared plus 9x plus 1 on our closed and bounded interval 0, 5. Okay, so we're just going to follow that strategy. Step 1 was evaluate the endpoints. So we can start with f of 0. F of 0 is easy enough. Put in zeros for all of these, you get 1. F of 5, well, we get 5 cubed is 125 minus 6 times 5 squared, which is 150. So 25 times 6 is 150 plus 9 times 5 is 45 plus 1. So it looks like we have what, 125 minus 150 is negative 25 plus 45 is 20 plus 1 is 21. We get 21. So I'm just going to write this more simply right here. And I'm just boxing them because we're going to need them later to compare. There's the values of the endpoints. I just put them off to the side. Now I need to find the critical points. Again, critical points are the places where the derivative doesn't exist, where the derivative is 0. So we need to start by looking at the derivative. We got 3x squared minus 12x plus 9. We can factor this to be 3 times x squared minus 4x plus 3, which we can factor again to be 3 times x minus 3, x minus 1. So this is equal to, well, first of all, it's a polynomial. Polynomials are defined everywhere, so there's no places where the derivative doesn't exist. So we're looking for the zeros. F prime of 0, f prime of x equals 0 when, well, let's just write it 3x minus 3 times x minus 1 equals 0. And that happens when x equals 3. Oops, extra there. So this happens when x equals 3 or x equals 1. So I've got my two critical points, x equals 3 and x equals 1. So let's evaluate there. F of 3. F of 3 turns out to be 1. And f of 1 turns out to be 5. So I've got my critical points evaluated, my endpoints evaluated. Let's just compare. So I'm just going to write them in order. F of 0 equals 1. F of 1 equals 5. F of 3 equals 1. F of 5 equals 21. We've got two minimums, right? Remember when we first talked about maximums and minimums, we can have more than one absolute maximum minimum because each of these points, f of 0 is greater than or less than or equal to every other value of the function, right? It happens to be equal to f of 3, but it's less than all the other ones, right? So this function has two absolute minimums. F of x has absolute minimums at x equals 0 and 3. And then I want to say what that is with f of 0 equals f of 3 equals 1. And has an absolute max at x equals 5 with f of 5 being equal to 21. Okay, this is what we call the closed interval method, right? It's pretty straightforward. Check the endpoints, evaluate the endpoints, find the critical points, evaluate them, and just compare. Look for the smallest, look for the largest. Let's finish with a picture of this. Here's our function f of x. We evaluated at the endpoints. 5, input of 5 gives output 21. There's our absolute max you can see in the picture. And then we had, 0, we evaluated to be 1. Here was at x equals 1, the output was 5. And then there's the input of 3 equal to 1. So the endpoint and this point at 3 have the same minimum value. This local maximum at 1, 5 is neither an absolute max or an absolute min, right? It's special in its little region, but it's not the biggest point in this interval. Okay, that is it for this one. We'll talk more about how to determine local maximums and minimums without graphs in some later videos, but that's it for this one. Thanks, everybody. I will see you next time.